I'm trying this in Notability. It's my first attempt at using Notability. So you have a worksheet to do, and it's one you're picking up today. It's worksheet 1-2, potential energy diagrams, and it's pretty simple. I'm going to do a little bit of this with you, but this is very self-explanatory. I just want to make sure that you understand a few things here. So looking at our first problem, our first question is this endo or exothermic? And since my reactants start here, my products end here, we can see that this is endothermic. The activation energy of the forward reaction. If you'll take a look at the activation energy of the forward reaction, you'll see that we're going from right here to right here. The forward reaction goes this way. So I'm going to figure out this by taking 130 minus 50 is 80. And this is in kilojoules. And you can see that it's going this way. It's 80 kilojoules this way, so it's positive 80 kilojoules. Next, oh no, that's not what I really wanted to do here. Okay, it's working. What is the activation energy for the reverse reaction? When we're talking about the reverse reaction, we're just going to go this way, if you will, and we can see that my activation energy, if I'm going that way, will be 30 kilojoules. Next, we're going to look at we are going to look at what our delta H is for what is my enthalpy change for the forward reaction. So you can see in the forward reaction, we are having a plus 50 kilojoules for the forward reaction. And for the reverse reaction, we're going to have a negative 50 kilojoules. Then we're asked, is the reverse reaction going this way, endo or exothermic? And of course, that'll be exothermic. This gets a little bit harder to do here. Then we're going to talk about species. I want to get my highlighter out. Is this my highlighter? So my three species are there, there, and there. These are the three species. Which species forms the activated complex? And you can see the activated complex is X2Y2. That is the activated complex. Which species has the highest potential energy? And that is also X2Y2. Which set of species then will have the highest kinetic energy? And we're looking, I'm going to make a little note up here. The sum of kinetic energy and potential energy equals our total mechanical energy. So it's going to be our total. So as potential energy goes up, kinetic energy goes down. As kinetic energy goes up, potential goes down. So if my highest potential energy is right here, this is my lowest potential energy. Therefore, it'll be my highest kinetic energy. So my X2 plus Y2 is the species there. Which species or set of species has the weakest bonds? That'll be X2Y2. Which species or set of species has the strongest bonds? That'll be X2 plus Y2, because if it's got the lowest energy, it's got the strongest bonds. What is the delta H for the reaction of Y2 of this? The delta H of going from here to here. And that will be negative 80 kilojoules. And then we're asked finally, I don't know if this is finally. No. I'm going to have to move this way, move up and down. What do you think would be faster, the forward or reverse reaction? And explain. And I think my reverse reaction would be faster because it's got an activation energy. That stands for activation energy. Is much smaller. Which results in a faster reaction. Which set of species or set of species has the lowest kinetic energy? And the lowest kinetic energy would be the one with the highest potential, would be my activated complex. And then show the delta H for the forward reaction. Show the delta H for the forward reaction and the activated on the graph above. Okay, let me see if I can figure out what they want me to do here. So I'm going to go up here. Whoopsie. I'm going to erase some of this. Oh my goodness. Didn't really want to erase very well. Got to erase smaller pieces, I guess. Okay. So then I'm going to do my activation energy of my forward reaction is right here. There's my activation energy. Activation energy of my forward reaction. Then I wanted my activation energy of my reverse reaction. I don't know if I can change colors. Yes, I can. So here is my activation energy. Of my reverse reaction. Excuse me. Okay, so looking at this. As reactant particles get closer, approach each other before a collision, the potential energy goes blank and the kinetic energy goes what? So the potential energy goes up and the kinetic energy goes down. Because we're looking at the part of the graph, here's my activated complex. As the particles approach each other, right here, your potential energy is increasing, and as potential energy goes up, my kinetic energy goes down. As newly formed particles move away from each other, move here, move this way, the potential energy goes down while the kinetic energy goes up. As reactant molecules approach each other, as the reactant molecules get closer to each other, they exert repulsive forces. And as they move thus, as they move together, what does their speed do? Their speed will decrease, and the potential energy will increase. Because as they approach each other, we're moving this way. So we can see that their potential energy is going to increase. Then we have an activated complex. This is a species that's highly unstable. It lasts a brief moment, and it's at the, I'm going to call it the top of the activation energy hill. It's what exists right up there. And I think that's all of my first part here. So now I want you to take another, I don't know how long I've been working on this one, but I want you to take another 15 minutes and work diligently on this packet. You should be able to do, let me make this much smaller. You should be able to do all of this one. And if I think you can finish this in 15 minutes. So work on this for about 15 minutes. If you finish before 15 minutes, then go back and work on the rates one some more. There is a key available. So do some and check. As a note, do not, I repeat, do not just come up and copy it down. Think about what you're doing. Have thoughts here. Think about it.